off your phone.
I was checking progress book. I was looking at progress book.
Yeah, and you're probably texting your mom.
No.
Stop it. Stop it. Yeah, whatever. We're trying to teach them about covalent bonding.
Okay.
Here we go.
All right, well, welcome back to our next segment on covalent bonding. Today we're going to be talking about polarity with covalent bonds. So when atoms are bonded covalently together, they're each looking to gain electrons to help satisfy their octet rule. And so we measure the atom's ability to pull electrons towards itself by its electronegativity. And we learned about this in chapter 6 when we looked at some of the trends. As we know, every element has a specific electronegativity. It has a number attached to it that shows how much it wants to pull on the electrons. So in a covalent bond, the higher that value is, the higher the electronegativity of the atom, the stronger the pull is on those shared electrons between them.
That numerical value is actually printed on your periodic table. If you flip it over to the side of the periodic table, it's kind of the back side, and look at the little legend. It says right there, it says electronegativity. And you'll all remember that fluorine is the most electronegative element on the periodic table, and then I think oxygen is second, and chlorine is third.
Right, up to that upper right corner. The elements further to the right or up are the ones that are going to have the stronger pull on the shared electrons.
So this resulting pull or tug of war for those electrons, that's creating a pretty small but measurable charge difference at the ends of the bond. So if one side of the bond is pulling more than the other side, we can see that difference. And we call both of these ends poles. So poles of the bond are pulling and doing a tug of war on these electrons in the middle.
So one end is going to be slightly positive, the other end is going to be slightly negative.
And like she said, that slightly small negative charge, that's going to be the side or the pole where the more electronegative element is. So when you look on the periodic table at the two elements you have bonding together, two or more, you'll see one might have a higher electronegativity. The one that is more electronegative is going to have that negative charge. On the opposite side of that, the other pole, the less electronegative element, is going to have a small positive charge attached to it.
I'm glad you mentioned the fact that there could be more than two elements involved. This is about a covalent bond. So whenever we're talking about polarity of a bond, we're looking just between two atoms. Yes, there may be more in a molecule, we'll get to that, but we're looking at each individual pair of atoms first.
So the scientists are all about measuring this amount of polarity. One way to actually quantify this amount of polarity is to calculate the percent ionic character. What? Yeah, I know.
Percent ionic character?
Yeah, we're talking about covalent bonds, but if the difference between the electronegativities of the two elements is really, really large, then you're going to have a high percent ionic character, right? And then it's going to become less and less covalent. Those electrons are going to be shared not very well. They'll be really hogged by one element. If the electronegativity difference is really, really small, then you're going to have a very low percent ionic character. If you have two exact identical elements bonded together, like O2, that's two oxygens, the electronegativity difference is 0. So you have no ionic character, and we call that kind of bond a nonpolar covalent bond. There's absolutely no difference in one end of the molecule, or one end of the bond, compared to the other end of the bond. And then there are ranges in between. But this is how you calculate it. You take the electronegativity difference between the two atoms that are bonded together, and then divide by the larger electronegativity value, and multiply by 100.
Sounds like that percent error calculation.
Yeah.
Yeah, so very similar to that. Whoop. So we have a sample problem for you here, and as we'll talk you through that, I guess, in pictures, because we didn't plan ahead for this when we were recording.
I think there's also a pencast.
Oh, there is a pencast.
Of a couple of these as well. Yeah.
All right, thank you for watching. Make sure you respond to your video homework, and you probably need to go back to your lab and make sure you've done your percent ionic character calculations correctly, and we'll see you in the next video.